Hey there, this is Raimo, and this is part 11 of my Introduction to Rust series, taking it one step at a time. So this video is going to cover how to interact with the real world in your Rust code. So how to get access to your program's environment, how to get input into your program and output from your program, and then along with all of that, we're going to talk about how to handle errors. So a lot about what I'm going to talk about today comes from the Rust standard library. These two modules in particular, the env and the io modules of the standard library. And I'm only going to touch on these. So to get the full story, you're going to want to check out the documentation for these modules. So let's get started. So first we're going to talk about the environment variables your program runs in. Environment variables are one way to control your program's behavior through settings that are arranged before your program is run. One environment variable that's used quite a bit is called the path environment variable. This is used a lot, for example, with the dynamic loader when you have one program load another to locate the other program. Basically, the operating system is going to search all the directories that are listed in the path environment variable for your program to find the other program that you want to run. So to get access to this path environment variable, we're going to use the standard library's var function. The key we are going to pass is the path key. In other words, the name of the environment variable. And you see that this function is going to return a result. That's either a string or an error. Now we'll get into result a little bit later in this video. But for right now, we're just going to do this magical unwrap function, which gives us the string. And let's start by printing that out. Path is, okay, running that. We see that there's a group of folders here separated by colons. Now this may vary depending on the operating system you're running. On Linux, it's usually a colon. On Windows, it could be a semicolon. So Rust does provide another function we can do to split this path up. Let folders equal standard env split path of our path. Now split path is an iterator, so we can iterate on that for folder in folders, and we can print each of those paths. So running that, we see that the individual folders now we have access to. So again, these are the folders that your program's loader is going to use to find other programs that you might launch. Now you might have noticed something about these folders. They're not strings, they are PathBufs. What is a PathBuf? Well, it's possible that you can have non-Unicode characters in folder names, whereas in Rust, strings are always Unicode, they're always UTF-8 encoded. In order to interoperate with strings that are not Unicode necessarily, Rust has a separate type for this. And there's a subtype called path, just for working with the names of folders and files on the operating system. The larger type is called OsString. So if you ever see these types that look and act like strings, they are, except for they're a little bit looser. For example, if I were to just try to print the folder without using the debug trait, just the normal display trait, you'll see that it'll say folder doesn't implement the display trait. It's because it might not be possible to display it as a Unicode string. There's another way you can print out a folder. You can use the display function, which is specifically crafted to give you an object that does implement display. And as you see here in the help, it says that safely printing it might do a lossy conversion. Basically, if there are non-Unicode characters or data in the name of a file or folder, it's going to have to drop them. So let's move on to another topic, which is the command line arguments or the arguments to our program. We might, for example, want to run our program with some arguments like A, B, C, and 1, 2, 3, for example. How would we get access to those arguments? The answer is, again, through the standard env, we have our args. Let's change this to args. Args is an iterator, so we can say for arg and args. So here's where it gets a little bit different. Args does give you an iterator of strings, and instead of giving you a different type for the string because it might have non-Unicode characters in it, it actually does panic if any of the arguments passed are not valid Unicode. So you see that a little bit of difference in behavior here between some of the functions in the standard library. And it deserves looking at the manual when you're not sure. Some things in the standard library will check for validity of Unicode, some of them won't, and the way they differ, usually it's in that if they handle non-Unicode, they do it by giving you a different kind of string type like OsString or PathBuf. And the ones that don't will just simply panic. Panic, again, just means crashing, so same thing. So here, let's just print out the different arguments to our program. Argument, and then we can use the display trait because it's a string. Now when we run this program, we actually get 3 arguments. Why 3? Traditionally, the first argument given to a program is the string which indicates how the program was launched in the first place. Usually it's the path and name of your program's executable, but doesn't necessarily have to be. It could be the name of a shortcut to your program. It's generally, you don't want to rely on that first argument being a path to your program. All the arguments past that first argument are the ones that are on the command line, so to speak. The string that was used to launch your program is divided by white space characters, and you're given each of those arguments one at a time through the standard env args. Now, there are lots of crates online you can find that make it a lot easier to work with environment variables. For example, there's struct opt, and I encourage you to look that up if you want to deal with your command line arguments, your program arguments a little bit more efficiently. But this is what the standard library does under all of that. Okay, so now that we know how in our program to get access to our program's environment variables, our command line arguments, how do we interact with the world more? So you might know that programs can interact with files. They can interact with a console through standard input, output, and error. And I'll go over each of these. We also know that programs can contact other programs on the internet through networking protocols. Let's go through each of these one by one. And let's start with the standard streams. So you might have heard of these: standard input, standard output, standard error. What are these? They are file handles that are given to every program, usually in almost every operating system, where one of these file handles is linked to the terminal you launch the program from, so it allows you to type input and it goes into your program. And the other two are for your program to give output. One is error-based output, like error messages. The other is non-errors. So we already have been working with the standard output stream all along. I just haven't said so. Whenever we use the println macro, we're taking that string and we're sending it to that standard output stream. If when we ran the program, we had redirected this standard output stream to a file using like a greater than out.txt, for example, now instead of seeing the output written onto our terminal or our console, we see it coming out into a file. So this isn't particular to Rust per se. It's something you can do usually in the terminal or shell of your operating system. And I'm just using it here to illustrate that these standard streams are not necessarily tied to a terminal or a console you're typing at, but they could also be linked to files. So if we wanted to go straight to the standard output stream, and rather than going through this macro, how do we do it? We can take standard IO, standard out, and we can write data directly to it. Now, the data has to be a mutable buffer, and that buffer has to be of bytes, not characters. So there's a little bit of conversion we're going to have to do, which is what's done usually in the println macro for us. But let's just do it by hand here. We're going to take this println and turn it into a format, which is basically the same as println, only it's not actually sending it anywhere. It's just constructing the string. And then we're going to use the asBytes method, which takes a string and gives us a slice or a view into that string as a list of bytes. One more thing we need to do is add the end of line terminator. With that, we should be able to do the same thing that we did with the print. Now let me show you what happens if we forgot to do that new line character, and I'll explain why we had to do that. Now all of our lines are glued together. Why? Because basically one of the other things println does with the ln at the end of that macro is it's adding that end of line terminator, which causes the line to be finished and go on to the next line. When we're going to the standard output stream directly, it's like really low level, we have to do that ourselves. So we have to actually put in that new line character. So let's say we wanted to turn this around and get input into our program from a file or from us typing at the terminal. As you might be able to guess, instead of standard out, there's a standard in. And let's say instead of doing a loop here, we just want to get one line of standard input. So input equal dot read line, which is a convenient function we can use. This operates a little bit differently. It's going to need to give us two things, the actual input, but it also needs to tell us whether or not there was a problem getting that input. And if there was no problem, it's going to want to tell us how many bytes it got. So we're going to have to provide a storage for that string. Let mutable input equal string new. And this input is actually going to be the number of characters. So let's just say n. And we're going to have to put this mysterious unwrap here for now, which we'll explain in a little bit. And we're going to need to borrow mutably our input here. At that point, we can actually print out what we input. U said, and then certain number of characters for input and n. So when I run that, you can see it's waiting for input. So I'll say something. Enter, you said something with the end line character and all that. 10 characters total. So of course there are lots of other convenient ways you can use standard input. I'll leave it to you to explore. Just look up the standard in Rust documentation. So that's how we interact with the standard streams. If we have files we want to work with, how do we work with those? So the file module in the standard library is what you'd use. Let's say we wanted to open that output.txt file we made and print out its contents. So the way we'd start out with this is to get a handle to the file through a standard fs file open. And then we put the name of the file in here and unwrap that because, as we'll talk about in a little bit, we could have a problem opening the file. Assuming we have the file, we are going to use a convenient wrapper for the file called a buffer reader. So let reader equal standard IO buff reader new, and then give it the file. And then with that buff reader, we can iterate over the lines of the file. So for line in reader.lines. Now, we've run into a problem already in that the lines method is not part of the reader itself, but it comes from the trait called buffRead. So like this says, we can do a quick fix to import that. So now we have a buffRead being imported, and each line can have a problem reading. So let's just, when we print out the line, we'll just print it after unwrapping it. When we run this, we'll see that it printed out the contents of our out.txt file. But let's say we wanted to take each line of this and change it and then write it to a different file. Let's make a new file. And here we'll use standard fs file create new.txt. So one easy thing we can do here is just say new file dot write all, as we did before. Take that string and call as bytes on it. We need to make our new file mutable in order for this to work. And because we're using this line unwrap twice, let's pull it out and make it line equals line unwrap. That way we can just say line here. Side note, in Rust, you can redefine variables. It's called shadowing. So this new variable is shadowing the old one. And so I use this as a technique to just change a value for the rest of the scope. So we're saying we don't really need to know about the errors for reading lines. We're just going to take that line. So if I run that as is, the new file has the same as the output, but oops, it doesn't have the new line. So let's add that in here. We'll just say format with a new line at the end, that line, and then as bytes. Run that, and now we have that. And so we can change this. We can say something like new. I'm not very creative, but just to illustrate that we can change the input to form the output. Ta-da! So of course there are lots of other methods of files besides reading and writing text, but this should get you off to a good start if you just want to work with simple text files. For more advanced stuff, again, look at the manual for this file type. Now, one thing I do want to show you here that makes it a little bit easier to work with is instead of having to convert our strings into bytes and then using write all and then having to worry about this new line, if we know that we're writing lines, there is a convenient macro similar to println. It's called writeln. And writeln works like println, except for the first argument is we borrow mutably the file. But otherwise, we can just take what we had put into the format and remove the new line. Running that, we get the same results in our new output file. Okay, so far we've explored getting our program's environment variables, program arguments, working with the standard IO, and reading and writing files. Let's say we wanted to explore outside of our program and get access to things on the internet. How would we do this? So two popular protocols used on the internet for programs to talk to each other are UDP and TCP. So I'll leave TCP as an exercise to the reader that there is a type called TCP stream, and there's a TCP listener for server side where you can make TCP connections and they work similar to files. But let's use the simpler UDP protocol in this example. So in UDP, we're simply sending packets, so simple small messages from one place to another. Rust provides a type called the UDP socket. So we can make one of these, like receiver equals standard net UDP socket. And we use the bind function to get a socket given an address we want to listen at. So we can use, for this example, the local host address 127.0.0.1 and then a :0 to tell Rust that for the port number part, we want the operating system to just pick one for us. And we'll unwrap that. And just to illustrate that we have a port number bound, we can get that port number back by printing it out here. We can say we bound port for listening receiver dot local address dot unwrap dot port. Running that, we see in this case we got port 47,226. So now that we have a port waiting to receive packets over the UDP protocol, How do we do this other side, sending? So it's a similar way we can do that here. We'll do it in the same program, although you can imagine this being done in a separate program, even on a different computer on the internet somewhere. Sender is in the same way. In fact, I'm just going to copy paste this. We're going to make a sender UDP socket. To send a message with this, there's a method called send_to. And then here we provide a buffer, so a slice of bytes. So in this case, we're going to introduce a new literal syntax to say hello world. What does this B in front? It turns it from being a string of characters to a string of bytes, which is pretty handy when you have literal byte strings, because we can actually see it in our source code, and yet Rust will treat it as a sequence of bytes instead of characters. And for address, we're just going to cheat here and do receiver.local address unwrap. So now we're not going to see anything because we're just sending, we're not doing the receiving end. To do the receiving end would be receiver.receiveFrom, and we have to provide a mutable buffer to store the data. So let's make one of them, like let mute buffer, and we'll just make it a simple array of 256 bytes. And what receiveFrom gives us back, if it's successful, is the number of bytes it received and the address of the sender. So let's put that here. N and sender address equal, and then unwrap that, and we'll print this out. We received, and we'll just print it as a string, and we'll also print the address of the receiver. So how do we take the bytes we received and turn them into a string? Well, first of all, we need to adjust the size of our array. So we're just going to make a new slice or view of that buffer from 0 to n. So I've touched on slices, but haven't really defined them precisely. But I think you can see intuitively here that if the original buffer is a 256 byte long array, this syntax is essentially saying take all of the bytes between 0 and up to, but not including n, and then just give me a view of that. So a subslice or a subview or subset of those bytes. To turn it into a string, we're going to want to say string from UTF-8 lossy in front. And then we can simply put the sender address here. Okay, and then I need to actually borrow our buffer mutably here. And then let's run this. So we can see we received our hello world message that we sent from the other socket, and it tells us the address that we sent from. Now again, the sender and receiver need not be in the same program or even on the same computer. As long as the two computers or programs that are running on them are connected through the network and you put the appropriate address on the sender and the receiver, it should be able to send and receive. So these are the very basics of input and output and program environment and arguments that you can do in Rust. A lot of crates are built on top of this that I recommend using those instead of these low-level APIs. So for example, we have the log, simple logger for handling when you want to write to log files. There's hyper request, tiny HTTP for where you want to actually connect to other computers on the internet through the web. And then there's a lot more to explore within the IO module itself when it comes to reading and writing. So there are traits like read, buff write that you want to explore. But again, this video taking it step by step, I want to only give you a taste and an introduction to it to set you on the right path. So for the rest of this video, I want to explain the mystery of what this unwrap is doing and how do we really handle errors cleanly in Rust. So if I simply mouse over this unwrap and read what it says it returns the OK value consuming the self because it may panic its use is discouraged, instead prefer using a pattern matching to handle the error case explicitly. So this is talking about the type result. Type result is how we represent errors in Rust. If we were to say handle this error where we might not be able to get a UDP socket, let's say instead of doing this unwrap, let's let the receiver equal the result of matching the result of this bind, and we'll have this fill in the match arms. We can see the result is really an enumerated type with two possibilities, OK and error or error. Think of the result type as holding on to two possibilities. Either you have the success possibility, in which case this is the actual receiver, so we would want to simply return it and let it be assigned to our receiver variable. Or the other possibility is that there was an error. And so we'll have an error object. This will have the error code, error message, other information that might help someone troubleshooting this program figure out what went wrong. In this case, let's say instead of continuing, we'll just print that there was some error, and we'll perhaps print out what that error has to say about itself, and then simply return from our main function. Put a semicolon here, and essentially we've done a rough equivalent to unwrap, except for the actual unwrap would, instead of printing, it would do a panic here, and then you wouldn't need to return. Again, panic is crashing, which is not always a nice thing to do in programs. Usually you want to handle the error. In this case, we're handling it by letting the user know about it and simply returning early. But in a program where it needed to recover, we might have it try again, or we might have it do some alternative in this case. So to force an error, let's make this port an unreasonably large number outside the range to show you what happens. So here we did catch an error, there was some error, and here we get some insight into the kind of error that it is. It's an invalid input, the invalid port value. So let's go back to the code that I had which dealt with files, because that's a little bit more interesting, because there are a couple different things that we could have gotten for an error when dealing with files, and I'd like to use that as an example to build upon. We'll remove the code that has to do with writing files for now. Okay, so in this case we have two unwraps, but there are actually two different kinds of problems that could happen here. One is that the file might not exist. So if I simply put in the name of a file that doesn't exist and try to run this, we'll get a panic because we unwrapped and it was an error saying that there was no such file or directory. The other error that could happen that I really can't show you easily is in the reading of a line of the file. If, for example, you had a file handle open and for some reason there was an error from the operating system when you tried to read it, like the disk was corrupted. In this case, this unwrap would have caused a panic. Let's say we wanted to turn this into a function which is a little bit easier and more convenient to use. So say instead of this being the main program, we actually have a main program which calls it, and so we'll call this read file. And in main, we'll have read file. And let's say that instead of unwrapping, we want to actually package these as two possible errors that could happen. So one way we could do this is to define our own error type. Make that an enum instead of a struct, and we'll have the two possibilities. An open error, and we could package the original standard IO error here if we wanted to, or a read error. And again, it has its own standard IO error. So the way that we would have this read file function return an indication of whether or not there was an error is to have it return a result with nothing in the success case and our error type in the error case. So result is always two arguments. The first is always what is the type when we're successful, and the second is what is the type when we have an error. So in this case, if read file is just printing out to standard output, we have no value to return on success, so we just put the empty or unit type. But if we do have some error to report, then that's where our error enum is going to be used. So in this case, let's do an unwrap down here. And one thing we have to add to our function here is when it gets to the end and there hasn't been an error, we have to actually return the success value. So in this case, it's okay with an empty value inside. This looks a little strange, but that's saying that the function was successful, but there was nothing to return. Okay, fix that dot down there. Okay, so one side note is that unwrap doesn't really work with our error type unless we implement debug. So one way we can do this is to use a derive attribute, which I'll explain in a future video. Essentially, this automatically implements the debug trait for our error type so that it'll work with unwrap, and if also it'll work if we wanted to print out the error. So let's actually handle these errors gracefully. If open returns a result, we can employ a method of result called map error, which is used to convert the type of the error if it was an error. Otherwise, if it's successful, leave the value alone. Now, just like map that we saw in previous video, it works with a function object or closure, and it's basically going to give us the original error and allow us to wrap that into a new type. So we'll use this like so. Error is our error open with that other error internally. Now, because this is getting a little bit too wide, I'm going to have to turn off inlay and so you can see. And like we did a little bit ago, we'll have to match on this, fill match arms, and if it's okay, we have a file. If it's an error, then we want to return that error. So let's do the same thing with the unwrap inside of the print line. We'll say here first, let line equal line.unwrap, just so that we can separate that from the print line. And then again, like we did before, instead of unwrap, we'll do a map error. And I'm just going to copy this code and paste it there and change open to read. And we'll also want to do a match like we did before. Fill the match arms. And here the line is unwrapped if it was okay. Otherwise we have an error and we're going to again return that error. Okay, now just running this program to make sure it's still working. We can see that it is. And if I change the name of the file to purposefully make it break, we'll see that that original file not found in directory is still in there, but it's wrapped by our error type. So this pattern is used so much in Rust that there are some convenient syntax around it to simplify it. This in particular, having this match, is handled by a special syntax character called the question mark. If we just remove that match, and again down here, remove this match, and replace this with the question mark, it's essentially the same thing. Think of the question mark as checking to see if the result was a successful or an error case, and if it's successful, unwrap it. Otherwise, take that error and return it. So running this, again, panics on open unless I change this out. Run it again and it should work. So another little trick that Rust is trying to tell us about here, about our closures that we're passing to map error. Essentially, you can replace it with just the name of the variant itself. So in other words, instead of saying take the error and map it in an error read, if we just trim this off and just say error read, and take this one and trim off the part of the closure and its argument, it works because you can think of an enum with variants that have single values attached to them as also working like functions that take a single argument, which is exactly what map error in this case wants. A function that will take an argument and return something else. So it's quite convenient. Now, most libraries that you'll see in Rust will define their own error types. It's so widely used, this concept, that there are crates out there like this error and anyhow that make this a whole lot easier and automate some of this stuff for you. So I definitely encourage you to look at those as well. I almost forgot there's one more trick you can do here, and you might have been asking while I was showing it, why do I still have an unwrap here? You actually don't need this unwrap because there's an alternate return value for main functions. You can return a result. So we can simply pass this along, remove the semicolon here, and guess what? It works. So in the case where we don't have an error, the program simply runs. And if we do make an error, like a wrong file name here, instead of panicking, it will actually just print out the error object that it gets before terminating, which is actually quite handy. Anyway, in summary, in this video, I hope you got a taste of how your Rust programs can interact with the outside world. We learned about the program environment variables, program arguments. We also saw how to interact with the standard streams, input, output, and error, and how to access the file system, opening, creating new files, reading, writing, and we got a little bit of taste of networking with UDP sockets. So again, there are tons of other crates out there for Rust that'll help make this a lot easier, implement a lot of common things for you. And there are a lot of methods attached to those types that I went through in this video, so I encourage you to look up the documentation for these to get a taste of what else you can do with them, because there's simply too much to cover in one video about this. So in the next video, we're going to be covering boxing and trait objects. I hope you'll stick with the series. Thanks for watching.